Hello everyone, welcome to this post-afternoon session. I hope you had enough food. Okay, so this talk will be about creating Android devices. It's a little different than most of the other talks in the conference, I guess. So basically we'll talk about how devices get made. Okay, so a little bit about myself. So I work at InnoMind Software, and we actually are in the business of creating devices, and we actually sell them to Indian ODMs. So that's our primary lookout at the moment. But later we are looking to expand and, of course, sell to more and more vendors, I guess, not necessarily people. So I'm the software architect there, and I'll talk about most of what happens in a very short time it takes out to roll out an Android device. So first of all, okay, before I even start off with the slides, I forgot to keep this slide. I want to know a little bit of the background of the audience. So are there any students around here? Just raise hands. Okay. Application developers? Oh, okay. Okay, I need to be aware of who I'm talking to most of the time. So you guys will be mostly talking about Android fragmentation. Okay, I'm going to give a different spin to it. I call it proliferation, not fragmentation. So we're going to talk about in this talk what I mean by proliferation. Okay, and there's something called reference designs which people use to churn out devices at a fast clip. So vendors give reference designs. So vendors as in silicon vendors, Qualcomm, Intel, Broadcom, TI, anybody that you look at. So we look at reference designs. We look at the typical customizations that people make on top of a reference design to give you the device that you hold in your hand finally. So you have a multitude of devices. What changes go into those designs to make the final device? We look at that. Then we'll talk about the whole workflow from concept to prototype. So it's a very short time. Then the most important part is I'll give a software perspective of the whole thing. I won't talk about creating a device is more than just doing the software. There's hardware, there are other things. Okay, so I'll restrict myself mostly to the software. And I'll talk about some lifesaver tools that we people use in our trades. Okay, so let's get started. So Android as a platform has proliferated a lot. So what do I mean by proliferated? There's a lot of devices and huge market share. Okay, so thousands. So I don't know how exactly Google doesn't tell us how many thousands. But there was this popular visualization of proliferation with the application called Openstreetmap. So what they basically did is they took the user base, figured out who are using what devices, and they put that in that visualization. So this is dated about May of this year, I think. Okay, so that shows some Samsung Galaxy S2, I think that this year. That's the maximum. But look at the total number of squares there. It's about 4,000 or something like that. And that's supposed to include custom ROMs, but that's very less in that whole picture. But you can see that sheer number of squares. Each rectangle represents a device. So they wanted about 4,000 active devices, just using their application by the way. So they will do more. Then the other person. So why is Android become so popular now? Everybody has a different view. So from a device maker point of view, somebody who's trying to make and market a device, Android is very easy to port. It's very easy to get out. I mean, compared to anything else, perhaps that was before it. Okay, Android is very easy to port. And Apache license usage in the user space actually makes sure that the vendor can keep a lot of things private. So they typically only release the kernel source code, but they will keep the user space code private. So some people have claimed that Android is open source, yet not open source because of this. Because even though there will be AOSP implementation, vendors' implementations are never released. So they are free to keep it proprietary. And the last reason, and perhaps one of the most important ones, is vendors have come out with a lot of reference designs, which allows people to just take reference designs and then do customizations on top of it and quickly release it to market. Okay, so what's a reference design? Right? So typically reference designs are complete Android implementations. Okay, so that means everything. We'll talk about what everything is later, but the reason behind vendors to make this is to make it easy for people to adopt their hardware. So when somebody wants to build a device, they're looking for time to market. So I showed a device to my friend here, and I told him it's ICS. He said, "Why doesn't it have jelly bean?" Okay, so that's the kind of impatience that's with people right now. So anytime it's released, they want it immediately. Okay, so time to market is very critical and very important. And of course, they are all hardware vendors. So for hardware vendors, they get their money by adoption of their designs. So the better they make their designs, the easier it is to use, the more they will be used. Who provides reference design? Your typical vendor, anybody. Okay, look at Qualcomm, NVIDIA, Broadcom. A lot of people provide their reference designs, which vendors can tweak. What's typically included in a reference design is all this. So even though I say Android implementation, it's more than just software, it's more than just hardware. There is a shell, there is a lot of documentation that somebody needs to customize that device. Okay, and there are certain things which are very hardware specific. So for example, something called bill of materials, which is what shows how much it costs to put together a device. Okay, so this is what is the cost for the touchscreen, this is the cost for the display panel, and so on. Okay, and there will be a lot of tools. So when somebody has to manufacture, tools are needed for that process. And also, of course, the manufacturing process itself is sometimes given by the vendor. Now, not all vendors will provide all of these, but the more the better from a perspective of ODM or OEM. I will say if a reference device is a working device by itself, I customize it, right? Why if it's not broken, why fix it? So there are several very good reasons. So the most common ones is that reference designs tend to be a superset of the whole market, several markets that it's targeting. So the most common thing is feature subsetting. So when somebody really modifies the design, they want to offer only a set or subset of the features that the reference design by itself provides. So it could be a lot of things. So for example, it could be no 3G modem. Okay, it could be let's save some money by cutting off some sensors. They're not needed. But it could be a lot of other things also. Let's do only USB host device. Okay, let's not do an SD card. A lot of things. You guys are aware of all of these anyway. But you may not see them that way. Okay, so the second and perhaps the most important thing done is cost optimization. So India especially is a very cost sensitive market. So a lot of things can happen in this arena. So for example, this can range all the way from let's buy this resistor from somebody to let's buy this chip from somebody else. Okay, to let's rearrange the way this board is made. So of course all this is hardware, so I'll not dwell too much about it. Then there's something else called leveraging economics of scale. So you may say, why is it different from cost optimization? So let's say you are a big vendor of something like for example HTC. Okay, so it's like HTC will save a lot of money. For example, I'm not speaking for HTC by the way. Okay, so HTC will save a lot of money if they use, let's say, the same accelerometer on all their devices, because that way they order the accelerometer in much bigger quantities and then do it. Of course, leveraging economics of scale makes it harder in this sense to have more differentiation. But those sort of things are quite common in things that people don't observe. So for example, on a display panel there will be differentiation, but on the accelerometer it will all be the same. So if you actually study the Android accelerometer source code of several devices, you will find that they are all mostly using the same thing. Okay, I won't name what it is. So the last one is differentiation. Everybody wants to talk about it, but very few people will do it. Right? And of course, we all know what differentiation is. It's the things that really make the difference, but they also cost the most money, so less and less people actually do it. Okay, so this is all the reason why somebody breaks and remakes an existing working design. Okay, so what has changed? We need a healthy list of things. So, look at this chart. ID is industrial design. That's the shape, the plastics, the weight, handles. Okay, where are the buttons, and so on. And on the lowest end, we have the processor model. So these things are typically made. Okay, so if you look at the lower part of the slide, you will find the items that have the least number of vendors. And if you look at ID, for example, even somebody in this field might do, I mean, he will claim to do it for you, but he cannot do a good job. You will realize that only when it goes to production. But it happens. So basically, that's why I labeled the lower parts selection, where the top parts customization. So we as Indians, we want to customize everything, right? Most of the time, all our houses are customized. But when we are trying to build a device, it's not always like that. So there's one item that I want to point out, which is memory. It's not in the middle. So it's very hard to change memory also. So even though memory is above graphics, it's typically much harder because it's a very tight intercoupling between the memory and the processor. So, but it's still possible to change it. So things like display and touchscreen are going to happen the most common, most often, and there's a good reason for it. That's because they constitute the majority of the cost. Okay, so now I can't give you a percentage because the percentage will vary between device to device, but majority of the cost, the majority of the power is also of course eaten by that. So, and panels, the quality of a panel is also a little harder to evaluate. It's not as simple as just looking at it. So, a lot of complicated things going on there, and most people make trade-offs there. Even the touch screen. And camera modules, of course. So, here's a typical workflow. So, basically what happens, let's say you are an OEM or ODM or a small time, somebody, let's say a small design house, and you either have a client or you are, let's say, doing something specific for yourself. So, for example, one of the first talks we had was about security, where they actually had their own device, which they were bundling with the application. So typically, that's what happens. As a value add, they will install an application and give a tablet. So the tablet has to be cheapest, right? It has to cost no more than it should, because the content is the key. Okay, so it doesn't need a very big design house to actually do a design. Of course, doing a quality job, I'm not going to talk about that. It'll take me a lot more time. Okay, so typically you take a reference design from one of the vendors, and you take the project goals, which could be anything. It could be reduce cost to give the best quality, to somewhere in between, or it could be something like, I want a HD screen, or I want 2 GB internal memory, or 1 GB of RAM. I want a 3G modem. So these are the kind of feature lists that people typically come up with. Okay, so quality is typically a part of the implementation. Specs are what typically rule. So based on the reference design and the project goals, so you can evaluate the reference design from a hardware perspective and a software perspective. You come up with a change list. So most of the things are provided by the reference design. So let's say I want to reduce the cost of the device. Okay, a simple thing I would do is I would take another cheaper display panel, which may not, have all the nice characteristics. If you look at it from all angles, it will not show the same colors. It may have a cheaper touch screen. Okay, and they are fairly easy to make because they are connected using standardized interfaces. Okay, so people change the components, making sure that they are compatible at the hardware level. So that's key, because not all reference designs will let you use all kinds of devices that you want to stick onto it. It may be cheap, but it doesn't mean it interfaces. So people have to be careful. So that's done first, and they make a change list which says this is what we are going to change. And at that point, the whole thing works off. So there's ID design, which is the shell and all the other things. There's hardware design, which is the board and electronics. And there's software design, of course, that most of us are familiar with. So Again, the next slide is only going to talk about software design and software design, but I'll talk briefly about ID design and hardware design as well. So there will be one or two hardware designers in your team who will execute this change list in the hardware. Okay, and after they are done, the board is sent for fabrication. So after a few weeks, you get a fresh board. That board has to go through something called a bring-up process, where both the software and the hardware guys are involved. So basically, that's the hardware specific part of debugging. So then you figure out whether the whole components are attached properly, whether somebody else made a mistake in the wiring, and so on. It's very valuable stuff. So that's called bring up. And after that follows something called tuning, where you make it ready for a demo. Okay. So many a time what happens is people in this business of creating devices are constantly pushed for demonstrating the device. It could be at trade shows, it could be to customers, or it could be internal management if it's a very big company, for example. Okay. So there is constant pressure to give a working, functioning prototype, the sort that can be used in trade shows, the sort that can be used in demo booths, shown to management. So it should work reasonably well. It should not crash every day or just press the power button. Okay. So there's a lot of work that happens in the tuning part. Okay, and then you get a prototype when you integrate it with the ID. So that also seems very simple because you may think, oh, well, after all, it's a shell, so you take this and you put it inside. But for those of you who have actually done something physical, as in creating something physical, you know that it's hard to get things lining up properly. So there will always be gaps, there will be quality issues there. Okay, so prototype plastics that you choose may not exactly line up to the kind of expectations people have. So it might seem like a plasticky device, whereas a production device always seems solid. So a lot of such things happen. And when you integrate the idea and the bring up brought up board, which might happen with some people doing some soldering to accommodate hardware issues, you have a prototype device. Oops. Okay, so what are the typical challenges that happen here? So as I was mentioning many a time, there are very short timelines to get most of these done. So the hardware vendor gives you a reference design, which they claim that it works perfectly, it's stable, and whatnot. Okay, and now the team which actually started making the derivative design has all the challenge of proving them right. Okay, so typically from taking a reference design to getting a first prototype out, there's the time gap could be anywhere between 1 to 3 months. Okay. So limited expertise. So it's not like people who are doing this have been doing this all their lives. Okay. They may come from, for example, a different background, or they may not have Android expertise, for example. Some of them may know Linux kernel, some of them may be from some other embedded background. Okay. And there's always scarce resources because people want to do more with less nowadays. You may not have the luxury of a large lab to test things. Okay, so certain things are very hard to debug. You will not have a large lab to test those. There's very sparse documentation. So most of you may not have read hardware data sheets, but believe me, they suck. Software documentation, way better any day. Okay, so there's something called a 2-line I2C interface. It's just 2 wires, and the kind of havoc that they cause in just those 2 wires, you just won't believe it. Okay. Every data sheet, everyone is supposed to be a semi-standard. It's mostly an electrical and a little more than an electrical standard. Every data sheet of every vendor, okay, what they do is they describe the same thing again in their data sheets. Just 2 wires. And I2C is the interface which is typically used for touch screens and sensors and those low-speed peripherals. So documentation is very sparse. It can be erratic. Okay, so for example, a board description file will say these 2 pins are in this way. So you wire it up that way, and finally your device doesn't work. Then you debug it using your probes and oscilloscopes and whatnot, and you figure out that the guy's documentation was incorrect. At which point you can't blame anybody but nobody. Okay, so hardware, software, co-design is what typically happens in these phases. So somebody makes a board in the hope that it will work, and they hope to have enough space to get it debugged and out before the timelines if they're not. And last one is the fragmented support part. So just because you got a reference design from a vendor doesn't mean that the vendor supports everything. So for example, something is not working with your device, let's say a touchscreen is not working, you can't go to the vendor. They will just say, it's the device, it's between you and the device, you guys sort it out. I2C is working, that's fine for us. So I2C is the interface which communicates between the processor and the actual touchscreen. So that's how it works. And finally, language barriers. Most of you may not have spoken with people in China. Perhaps the hardware people are the ones that, except if you are working in Hawaii, by the way. Okay, so most other software engineers I don't think are exposed to China except the Hawaii engineers, at least in my experience. Okay, but if you come to this hardware software integrated kind of business, you will see data sheets in Chinese. Okay, so all of a sudden your tools become, instead of doing Google search, you will do a Baidu search and then followed by Google Translate. So that's the sort of thing that you would expect. Okay, so you ask the vendor for, I want a data sheet for this so that I can program this part. He will say, here's the data sheet. What's inside the data sheet? Yeah, inside the data sheet is a lot of Chinese characters. And that will be in PDF, so you can't even translate it. So good luck to you. So you say, I asked you in English. Okay, so good luck with that. Okay, so what kind of changes get made? Whole lot of changes. So we're running out of time. So any questions? In the 9 minutes one. Yeah, no, I think it's fine. Yeah. There's only one slide. So there's a gamut of changes which get made. So depending on the sophistication of the vendor and the amount of resources they have and the kind of market that they're catering to. So all these are important. So a common complaint is, for example, that the Chinese vendors just change the shell and sell. Okay. So that happens too. So it all depends on what the requirements are. So it's not like us saying everybody should make the best device possible. They don't, because that's not their business. It costs money. The moment you produce a few devices, your bank breaks if you're not careful. So hardware designers are much more conservative. Actually, software designers are not that conservative and constrained. Hardware designers are always very constrained and conservative. So that's why we see these megahertz races, the core races, and so on. Continuous improvement is what they want to call it. Okay, so all sorts of changes get made. Starting from scaling, which is the cheapest, which is you just change the shell. Okay. Then going on to do something which they call value add, which is changing the desktop bus that bundling some apps. Okay, and that might involve a little packaging software change. Okay, so if you change the ID, you have a little bit of implication in terms of mapping the keys. So for example, you may have a few keys for volume. The reference design may have keys for volume control. Your device doesn't have keys for volume control. If that's the case, then you have to do some sort of changes here and there. Okay. Then sensors. So sensors are, from the Android software perspective, they're mostly plug and play. So you just remove them, you make sure that the driver is disabled and it doesn't fail to load and so on. And it won't show up in the framework layers. And then there's basic I/O, which is display and touch. The reason I'm calling it basic I/O is because the interface themselves are not very complicated in terms of protocol. So you just dump an image into a display and it shows the display. It's a fairly simple device. But if you compare it with Wi-Fi, PT or some GPS or something, GPS is not that complicated. Wi-Fi, PT perhaps. Okay. So the lower you go down this list, the harder it becomes to make those changes. But Android is fairly modular. So Android has framework layers, it has HAL layers, which are hardware abstraction. For complicated layers like for Wi-Fi, for any radio frequency stuff, they have something called radio RIL. What is that? Radio interface layer. Okay, so you can make the changes in a very modular fashion, and if you look around on the internet or even in some, for example, my earlier talks, you will see some examples. And the last category is what I call the unknown or uncharted category, which is non-standard functionality. So some of it seems standard, but it really isn't. So for example, HDMI, okay, it's very non-standard functionality. You will see a lot of tablets with it. You will see a lot of tablets with support, for example, a USB pen drive. But they will all mount them in different directories. They will do things in a different way, and so on. So typically what happens is something is non-standard. You have to create everything from scratch needed to support it, all the way from the kernel to the framework levels. Okay, and that results in more fragmentation. One second, the questions are there. Please hold it. Yeah, we are almost up. Yeah. So that's how it goes. So the easiest ones is getting, most difficult ones is the non-standard functionality. And we'll skip the detail because we're out of time. These are the lifesaver tools that we typically have. So if you have an open board without a display working, you will use VNC because the rest of Android works just fine, for example. Okay. Serial port SSH, all of the typical Linux tools. No surprises. And certain real hardware debuggers are also used based on something called JTAG. So if something is really wrong, this is what is used to fix all these things. Okay, questions?
So the thing when you showed that list of changes, can you go back to that?
Okay.
So one thing I've seen is that sometimes apps crash because certain devices, they're missing libraries, like Android libraries, but I haven't seen that in this list. So do manufacturers, like I think Micromax in some cases has done some optimization.
I'll tell you what can happen. What will happen is they won't have the part, but they won't have disabled it in the list which is exposed to the user space. So the user is able to install the application because it reports there is an accelerometer, for example.
No, it's the opposite. At the user level, I'm trying to call a library, an Android thing, but it's basically says class not found. I get some exception.
Is it for a device?
No, it's a general. Well, it is for a device. I mean, eventually it's.
Yeah. Right. So that's what I was talking about. If you have a device which is missing, so what will happen? Hardware guy will say, okay, I've chipped it off. I've saved the cost. The software guy has to go there and make sure it does not show up in the list of sensors supported by the device.
No, and what he's trying to say is parts that are not even related to hardware. It's just
that I can't really say anything about. So it could be anywhere, right?
No,
it's part of the process.
Is that something that manufacturers do, right? So here you talked about things like skinning in one lane.
Yes.
Have you seen optimizations where a manufacturer says, hey, this library is too big, let me take it out of this phone. This phone has not active.
Not yet. I would say not yet. Yeah. Because this is a low end game I'm talking about. Remember, high end is a totally different game. So yes.
There is one concept of certification as
correct. So that's after the prototype stage and out of the scope of this talk. So we can talk about it later. Any more questions?
What kind of minimums do your manufacturers work with?
What do you mean?
So if you're going to do a prototype and you're going to do a custom device, you will need to guarantee some minimums, right, for your manufacturer to be interested.
I don't think so. Depends on the vendor actually. If it's a really big player. So for example, let's say a year back you wanted OMAP for your device. They would ask you how many million you want to sell. No million, no device, no chip. You don't get it. So that's where actually some parts of the ARM ecosystem are better because you get access to those. And they're used to working with the small players, so chances are high you get it.
So now you can get OMAP devices.
I think now OMAP is a different story. Yeah. Now OMAP is a different story, right? They've duplicated it and done something else. Any more questions? Okay, thanks for attending and hope it was useful. I know it was not technical, that's not my style. That's all we can cover here. Any more questions we can